Bueno, vamos a comenzar. Bueno. Puntualmente. Okay, so we start the session of the afternoon with Alice Hoff, Idea Theoretic Study of the Milner Vibration.
Thank you. First of all, I'd like to thank the organizers for inviting me. It's a great honor to be here, and to wish Pepe, of course, a happy birthday. And I hope you enjoy the talk. So all right, I'm going to tell you something about the Milner vibration, and because I know we have sort of a diverse audience coming from different areas of mathematics, I'll start by saying some things that probably quite a few of you already know, but let me just introduce so people know. Okay, first, something that probably almost everybody knows: if we have a holomorphic function and we look at a point where this holomorphic function is a submersion, and we zoom in, we look at a small enough open neighborhood, then up to some change of coordinates, f is just a coordinate projection, right? Nothing really interesting will happen. This is what happens at points where f is a submersion. And then if yes, in this case, this just means any of the partial derivatives fails to be 0, then you get this picture: everything is boring, nothing is interesting. Well, that's an exaggeration, but so if all of the critical points are 0, if all of the partial derivatives are 0, you have a critical point. This is when f fails to be a submersion, and then the fiber through this point, through this critical point, will be singular, right? So and the surrounding fibers will still be smooth by, if you want Sard's theorem or something. So you will have this situation where you can't anymore just have this projection of a product, right? It's something more complicated is happening. But so you have this central singular fiber. But if you look at this picture, you can maybe kind of start to get a sense that if you throw away this central singular fiber, the rest of these guys, at least close enough to the value I'm considering, will all look the same, right? They just at the very least, in this particular picture I'm showing you, you can kind of see that they have the same shape. And so this turns out to be true, and this is what we mean when we talk about the Milner vibration, or at least the Milner tube vibration. So here it is sort of stated formally. If we have this holomorphic function germ, and we take a representative on a small enough open ball of radius epsilon, and we look at a disk in the target, so we look at a small enough delta, and we only consider values near that delta, and we throw away our central, potentially singular fiber. This restriction of f to this space now is a smooth, locally trivial vibration that does not depend on the choices we made, right? As long as we choose a small enough epsilon, a small enough delta relative to that epsilon, we get this well-defined kind of local smooth fiber of f. And in fact, we get all of these fitting together into a vibration. This is called the Milner vibration, or the Milner-Ley vibration if you're feeling fancy. And its fiber is called the Milner fiber. Okay, this is the object we want to study, and sort of the goal, of course, is to say, well, if I have some holomorphic function, and I may as well say holomorphic function germ, I want to know what is the Milner vibration doing? What does it look like? And in particular, it would be great to find some effective way of computing, ideally maybe the homotopy type, but even the homology. Once you know this, also maybe the monodromy of the vibration. So these are things we would dearly like to do. Of course, many people have worked on this for a long time, and it's not so simple. But we're going to see what we can say toward this end. So okay, if we think back to that slide where I had the picture where it was a critical point, I made some claim that, well, the smooth fibers that you get, they look like they're somewhat related to the singular fiber in some way. Their shape looks like it's related to the shape of the singularity and the shape of the critical locus. And as sort of a first step toward making that idea concrete, I mean, not historically first, but in the terms of the presentation that I'm giving, I guess first. There's this theorem by Kato and Matsumoto that says the dimension of the critical set will control something about this smooth fiber that you get. So somehow, if you look at the collection of critical points, in this case, we're saying, well, the dimension of this will control the connectivity of this smooth fiber. So if S is our complex dimension of the critical locus, then the Milnor fiber, the fiber of this fibration, is N minus S minus 1 connected. And in particular, just as a little bit of a consequence, since FF is a Stein manifold, this means that the reduced homology will be concentrated in degrees between N minus S and N. So this is sort of a first thing that we can see where the shape of the critical locus is really telling us also something about the shape of the nearby smooth fibers. And yes? Constraints in what sense? So I think the range of Betty numbers you can get is fairly broad. I know there are examples where only sort of the lowest possible one occurs and the rest are 0. There are examples where only the highest possible one is non-zero and the rest are 0. I don't know if I know off the top of my head that there are any general constraints. There are certainly, there are these attaching results of Ley about, if you take these slices by hyperplanes, you can get some numbers of N cells in building some homotopy model of this fiber, and then of course, these will give you some bounds on the Betty numbers, but beyond something like this where you're going in and computing some polar multiplicity like that and using that to get a bound, I don't know if there's any constraint beyond that. Other questions, comments, concerns? Cool. Okay. So I guess the kind of idea that I want to talk to you about today, and what I'm. Oh no, I said this. Oh, what is a Stein manifold? So a Stein manifold, to be simple, I guess, is you can think it's a complex analytic manifold that you can embed in complex analytic Euclidean space, and through some Morse theory, it turns out that if you have a Stein manifold of dimension n, then it has the homotopy type of a CW complex of real dimension n, and in particular, you can't have higher homology than this. So this is the only reason I bring up Stein manifolds. They won't be super relevant for the rest. But okay, so, oops, sorry. So this, to talk about today is this idea of, well, we have this critical locus, and we're trying to use the critical locus and the shape of the critical locus to figure out things about the shape of the smooth fiber. And so the thing with the Jacobian criterion is that the critical locus we can consider as a set, a subspace, a germ of a subspace, but we can actually do a little bit more. We can kind of take a page from the book of algebraic geometry and give it this non-reduced structure that I'll say more about as we go through here. But so there's this Jacobian criterion that says if I have a map of of schemes or of complex analytic spaces, and it's a finitely presented flat map of pure relative dimension n, and if that's too much of a mouthful for you, really the special case we'll care about is this highlighted in green. If I have a holomorphic function, holomorphic function from c to the n plus k to c to the k, and the fibers are n-dimensional, then it will satisfy these conditions. So if if you're not so much an algebraic geometry person, you can just think about this and you'll be fine. So okay, if I have a map like this, then if I take the nth fitting ideal of the sheaf of relative Kähler differentials and I take this ideal, we'll call this the Jacobian ideal. If again, that kind of thing is not your cup of tea, and in our example here, you can just think the ideal of k by k minors of this Jacobian matrix. That can be our definition if you want. Then if I take the vanishing of this ideal, set theoretically, this is exactly the locus where our map fails to be smooth, which is to say, the critical locus of F. So we have this, in general, I guess, let's see, n plus k, choose k, but of course it may be that some of these are redundant. Right, yeah, I think the sort of minimal number may depend, may vary. Yes, so this Jacobian ideal set theoretically cuts out the critical locus, but may not cut it out as a reduced complex analytic space, right? There may be some extra structure where it really is helpful to remember, if you want, not just the radical of this ideal, but the ideal itself. And as an example of this, if we look at the case of isolated critical points, so if I have a non-constant holomorphic function germ, and the origin is an isolated critical point of this function, of course, set theoretically, the critical locus is then just a point, but as we see, it comes with this extra structure from this Jacobian ideal. And the thing that Milner proved in his original book introducing the Milner fibration, and then he proved it for polynomials, and Ham mopped it up for holomorphic functions. But in this case, the Milner fiber will in fact be homotopy equivalent to a wedge of n spheres, and we can figure out what the number of those n spheres is. So we have this Milner number, which is, if you want to be fancier, this is the length of the structure sheaf of the critical locus, which is to say we just take we take our Jacobian ideal, we mod out our algebra of germs of holomorphic functions by this Jacobian ideal, and we look at just the dimension over the complex numbers. So this is the Milner number, and somehow in this isolated case, it tells us exactly what is the homotopy type of this Milner fiber. Right, so we were saying we were interested in studying the Milner fibration via the critical locus, and this says, hey, at least in the isolated case, if we consider this non-reduced structure, then in fact we can get pretty much what we want, right? We can find the homotopy type. So now, of course, this sort of raises the question: what can we do if this S is non-zero, right? If our dimension of our critical locus is more than 0, if the origin is a non-isolated point of the critical locus. And so ideally, what we would like to do is find a formula like this would be great, right? Where we just, we compute some maybe scheme theoretic invariance of this Jacobian ideal, and that tells us the homotopy type, or even just the homology of the Milner fiber. This, unfortunately, I think is still a ways out, but today what we'll discuss instead is some relative version of this result, where you can use this kind of a philosophy to control the behavior of the Milner fibration in families, in a way I'll elaborate on in just a moment. And that's maybe a natural point. At this point, any questions, comments, concerns still, or still good? Cool, okay. So I'm saying we should consider the behavior in families, so let me do just a little bit of setup and sort of establish the framework we'll work within. So we'll again have this non-constant holomorphic function germ from C to the n plus 1 to C. And we're now going to consider a deformation of this, right? We have our non-constant holomorphic function germ that we want to study, and we want to say, hey, what happens if I perturb it a little in some particular way? So now we let our big F be this map from C to the n plus 2 to C, where we think of this as giving a family in this way, where we say, well, if I fix some particular value of t, I think of that as giving me this holomorphic function f sub t, where t is our parameter. And we, of course, to have this be a deformation of our original f, we let f0 be f, and then just also as a bit of a notation to establish now, I'll say that pi is the projection to the parameter space. Okay, so we have these deformations that look like this, and now we want to know, okay, I have some deformation that I've cooked up, my favorite deformation, maybe someone walked in the door and handed me a deformation, whatever, I have it, and we know by the definition of the by the definition of the Milnor fibration, so I'm really just restating things here. If I look at t equals 0, right, and I take a very small value of my function, and I look at the fiber over that value, and I intersect this with a very small open ball, like so, by definition, this is the Milnor fiber, as long as I didn't take v equals 0, right? So as long as this fiber over v is in fact one of the smooth fibers. And so if we're interested in knowing which deformations are useful in studying the Milnor fibration, what we really would like is to now be able to say, well, if I wiggle t a little bit, so if I have my t very small, and relative, again, maybe to this epsilon I've chosen, if I have this t very small, and I look at now this fiber instead of f0 of ft, intersected with this ball, and I see what that is. The condition we want to ask about is this going to be the Milnor fiber? Again, as long as this is smooth, right? Because of course, if it's not smooth, it's not going to be the Milnor fiber. But we want to know, well, if I just nudge a little bit and I still look at a nearby smooth fiber for a different value of t, is that still my Milnor fiber? Can I still use this to study the original f? So this is the condition we want. And as a bit of an example, just to convince you that maybe this question is interesting, this condition is not always going to be satisfied. So, for example, we can take a very simple function of 3 variables. F of x, y, and z is just x times y, and we deform it a little by adding this or subtracting this t times z. And then this condition will fail because it's not too hard to see that the Milnor fiber of your original guy is homotopy equivalent to a circle. But on the other hand, as soon as I have a small non-zero value of t, this smooth fiber, if you want, at v equals 0, is just the graph of some function intersected with this open ball, and that turns out to be contractible, and it's still smooth. So here we have a deformation where we don't get the Milnor fibration back for some reason. And so the idea now is we want to do something to prevent this using this idea that the Jacobian ideal will be important. That somehow looking at the critical locus in terms of this ideal that cuts it out will tell us what's going on with the Milnor fibration. So here's a theorem. So we keep our setup of our function and our deformation and the projection again to the parameter space. And now we look at the critical locus, but also how the critical locus is embedded in its sort of surroundings in the ambient space. So there's this notion from algebraic geometry of an infinitesimal neighborhood where, if I have a space cut out by some ideal, I look at all of the different powers of this ideal and what the spaces that these cut out, and this is set theoretically, the same because it's the same up to a radical, but you get somehow more and more information about the surroundings of your space. So these are these infinitesimal neighborhoods, and I want to look at these, these infinitesimal neighborhoods now of my function from my family crossed with the projection to the parameter space, right? So I want a fiber of this f cross pi to be one of these fibers of f sub t for some t. And so what we're going to ask is, if we take this critical locus of f cross pi, which is the family of critical loci of the different f sub t's, and we require it to be flat over the parameter space, which is some condition from algebraic geometry that tells us that this thing varies consistently. This is like the algebro-geometric notion of what it means to be a deformation. So we have this condition that says somehow this critical locus, this family of critical loci, is a deformation over the parameter space, and all of its infinitesimal neighborhoods are as well. This is our hypothesis. And equivalently, if you're a busy person and you don't like to check countably infinitely many hypotheses every time you use a theorem, there's also one object called the normal cone whose flatness you can check, and it's equivalent to check this. But either way, so you check either of these conditions, you verify this idea of the critical locus being a deformation in some embedded sense, and then it turns out that the condition we wanted holds. So the So we can use this deformation, in fact, to study the Milnor fibration. And to be very concrete about this, this says, well, you know, if I take my algebra of local holomorphic function germs and I mod out by the partial derivatives of big F with respect to the variables other than the parameter, and I take all powers of that ideal, I just want to check that T is a non-zero divisor in that quotient algebra for all these different K, or equivalently in this associated graded algebra, just all on its own. So, you know, because we're over a one-dimensional base here, somehow it's checking flatness really boils down to checking this algebraic condition about T. And just a couple of notes about this. First of all, this associated graded I mentioned, and I thought I should go ahead and throw in a definition in more detail. This is just this graded algebra you can get from a ring in an ideal, where it's, you know, in degree 0 it's R mod I, and then in degree 1 it's I mod I squared, et cetera. And, you know, there's some natural graded multiplication that comes from this in sort of the, like I say, the natural way. There are no real choices here. And so this is this algebraic object, and then its spectrum is this thing called the normal cone to the vanishing of I in the spectrum of your ring. In this case, you know, we're looking at the normal cone, like it says, to the critical locus in the ambient space. So this is this object. And another note, it is possible to relax the hypothesis slightly in a couple of different ways, and it's you know, just maybe for the purposes of giving a talk, it makes the statement unnecessarily complicated, and we don't really have time to go into it. But this is not, you know, exactly the best statement you can make. And then also, you know, again, I've simplified for the purposes of exposition. But, you know, the conclusion is also slightly stronger than just the condition star. Really, we get this Milnor-Ley fibration in the sense that, you know, Juanjo, for example, was discussing earlier, for this F cross pi, right? So we get some fibration result, and then this, as a result, our condition that we can study the Milnor fibration in this way kind of falls out of this. And also, if we wanted, we could use this to find information about the monodromy as well. And so, okay, I guess I'm maybe slightly ahead of schedule, but I thought I would close by just giving an idea of proof for the people who are more in this area with, you know, many terms I think sort of left out and not defined. So if you are not so much a Milnor fibration person and you're still paying attention, feel free to stop. But the sort of the goal is, okay, you know, we want to get this like I say, this Milnor-Ley fibration, and we usually do this kind of thing by applying Thom's first isotopy lemma and showing this transversality of smooth fibers to the boundary sphere, in this case, this family of boundary spheres over our parameter space. And as is very typical, we want to rule out these failures of transversality by cooking up some stratification that satisfies this Thom condition, or, you know, at least partially satisfies this Thom condition. And the idea is, well, this Thom condition says something about limiting tangent spaces to your fibers and to your smooth fibers of your function, and this can also be phrased in terms of instead limiting conormal lines, and so this relative conormal space, which gives you this union of limiting conormal lines, can be used to rephrase the Thom condition, right? There's a way to say the Thom condition in terms of this space, and then the sort of the meaty piece is that the behavior of this relative conormal space under specialization. So if I have this relative conormal space of my whole T star F cross pi, this relative conormal space of my whole F cross pi, and I want to think about what happens when I restrict this to pi equals 0, restrict this to my original function. The relationship between this guy and the relative conormal space just of the F0, you know, my original function, is controlled by the failure of flatness of these infinitesimal neighborhoods of the critical locus, due to some form of a spectral sequence argument. And so you can, when you have this flatness hypothesis, you can then go ahead and conclude that the specialization happens in a nice way, and this allows you to find this stratification that satisfies the Thom condition. So I am slightly early, but that's what I got. thanks to everybody for listening, and again, happy birthday to Pepe. So the question was, is there a connection between this and the constancy of the Milnor number in a family? I would say not really, because it turns out that this condition we're asking about algebraically, like this flatness of the, if you want the normal cone to the critical locus, and this condition we're asking for geometrically, which is that this local smooth fiber will somehow stay constant. In the isolated case, where we can ask about the Milnor number, these are both always satisfied. So it's the constancy of the Milnor number, I think, is something, something not entirely related. I mean, I think there's something you can say about. Well, no. Let me not be overambitious. I think it's not quite so relevant. Yeah.
Yes? So if the function pi is not a parameter t, but is a general function, is possible to say something?
So when you say, I see. So it may be, but I think it would require a fair amount of extra work, because this like I mentioned, this specialization result about how this relative conormal space and its specialization to this fiber relates to the the relative conormal space of little f. This is something very specific to having this direction, having your parameter space be smooth and having this be the projection to the parameter space. It really says, like, I mean, I can even write it down. What ends up being true is, as long as you have this as long as you have this flatness hypothesis, then this relative conormal space of c to the n plus 2 restricted over pi inverse 0, this ends up being isomorphic to the relative conormal space in c to the n plus 1 cross this c, which is coming from the parameter space. So in this way, it's sort of, it's very special that this is a projection. I think it's not completely out of the question that you might be able to go in and modify the argument heavily and say more, but off the top of my head, I don't know exactly.
Thank
I didn't quite. Can you repeat again what is the Milnor fiber in the non-isolated case?
In the non-isolated case, so it is the same. So this theorem of Milnor, that if you have this polymorphic function germ and you restrict to a small enough open ball, and then you throw away the singular fiber, and then you look at just values very close, and you get a fibration. This applies actually even if your critical point is not isolated, because the critical locus will be locally contained entirely in this fiber of the origin, even if it's not isolated. So when you throw away that,
the critical locus is still in the fiber over 0.
Yes. Yes.
Oh, okay. So then it looks the same.
Yes.
Okay. Thank you.
Any other question?
Can I make a comment? Yeah. There was a previous question, and you repeated the question.
Yep.
Right? Is that something that they do at your institute? And
Oh no, it was just there was some drama about the microphone making it to the question after in
Okay.
time. So I thought
It would be
best.
wonderful if the speaker would repeat the questions. I mean, in an ideal world, that would happen, but because usually he answers the question, and many of the people in the audience haven't heard it, and
Sure.
and also when you formulate the question, it's like what you're going to answer, right? So
Cool, yeah.
This is very
Appreciate,
ideal, but I was
kind of people say so.
struck by the fact that you repeated the question, and so, thank you.
Thank you.
We meet in 15 minutes punctually.
Okay.
Yeah. Yeah.
Okay, thank you.
You know that now I understand why I like places like Oberwolf.
Who?
You like why I like Oberwolf?
Ah, yes.
Because Oberwolf.
In the first place, because all the photos and the things you never see.
Yeah. Now, the point is that you live exactly the same place where the conference is. So that when you are tired and you want to skip a tour, then you go home and lie a little bit
You
down.
are forced to work with people, whether you like it or not.
But
You are forced to work with others,
yeah,
whether you like it or not.
yeah. No, Oberwolf, this kind of Luminin, Bedlev, Messerai, this is just imp. No, imp is bad
Ah, yeah, why?
because you don't live there.
Ah, right.
It's like here.
Too many discussions with Rio.
Yeah. No, but the point is, imp is equally bad as here. Yeah. In Guanajuato, yes.
That's
But
fantastic.
you never live there. That still you have to. The best point of your work because you are there. You live in the same place. So if you are tired, you go and go to bed and just. Here you have to look on.
Okay, you are coming. Nice mosquitoes. Hello. Are you hot? I'm hot.
Nos estamos
Okay.
pronto. Nos estamos pronto. That's Portuguese, maybe. Nos estamos pronto. Are we ready? Okay.
Okay, it's time. Okay. It's my pleasure
Can you hear
to
me?
present last speaker of today's.
Oh, wait. That's okay.
Okay.
I'll wait.
¿No se oye? Ah. My great pleasure to present a friend of Cuernavaca and of many of us, a great mathematician, Dennis Sullivan, last speaker of today.
So I changed the abstract. I wanted to go back to my usual casual style, but I remember in 1982, Pepe was visiting France and was giving some talks, and Pepe offered to write notes, and he was working very hard on these notes. So I thought, I have to not just BS, about math ideas. I should prove something concrete. So he gave this pressure, very polite, indirect pressure, because you were doing the notes. And that was this theorem about finiteness of the all-fours, because even though it's an interesting result in terms of activity, it was just a translation of a result from one domain to another. So it was just a matter of doing it. So thank you, for that diligence. Okay. So let's see, where are we? Okay. So I remember hearing a technical version of what I'm going to write here, and I write the softer version that everybody learns much earlier. But I remember that it was Shafarevich maybe or something like that. He said, except for elementary exceptions, every Riemann surface is a Fuchsian group. And I was, what? I mean, you can take Cantor sets out of the sphere, that's a Riemann surface, anyway. But that's the sort of technical version that was only known after 1900, but it begins with, which is the one that is not so unfamiliar, but every oriented two-manifold admits, how do I say this? Every oriented two-manifold admits a coordinate chart cover with charts in R2. So I make a picture. So here's an arbitrary oriented two-manifold, and it's got a covering. Let me just do 3 of them, etc. And then here's R2, and let's say this is 1, 2, 3. So there are charts, 1, 2, 3, in R2. This is R2. And then on this piece here, which is the intersection of 1 and 2, well, it goes over to here. This piece goes over here. It also goes somewhere in 2. And then by taking, you start here, go back to here by 1 inverse, and then go over to 2, and you get a map from here to here, which is like the change of coordinates map. And then similarly, you have the same thing. This overlap here goes into 2, and also goes into 3. And then you have, go back to here, go over to here, and you get a map from here to here. And these are the transitions, or the change of coordinates. You could think that these open sets in R2 are glued together by these maps. And so that the transition maps, the transitions, are given by z goes to f of z, where you think of R2, x, y, c, x plus I, y, equals x plus iy equals z, and it's not the same. I give it by z goes to f of z, which is complex analytic, namely differentiable with respect to the complex variable. So this is a remarkable theorem that you learn quite early. Anyone want to give a two-line proof? What? That's not a proof. I'll give a hint. Well, and his student Riemann. What? 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 Wittgenstein? Well, I mean, one way is choose a Riemannian metric if it's paracompact. So I didn't say what manifolds are paracompact. Choose a Riemannian metric. That was his student, so he sort of knew about Riemannian metrics. And then he proved this for surfaces in R3, but he proved, his proof shows that any Riemannian metric is locally conformally flat. And then the Cauchy-Riemann equations, if you choose your charts like that and multiply them by functions locally to make the metric conformally flat, you could choose the chart to preserve angles. Then these maps, if they preserve orientation and angles, will be complex analytic. Okay? So Gauss would know this, although he needed his PhD students' formulation of Riemannian geometry to give it a modern proof. Anyway, this is quite remarkable for me. And then later they proved the uniformization theorem. So you could look at the universal covers, and they're either standard things because of complex analysis, and then you get a stronger statement about the one I said about, except for elementary examples, every Riemann surface is a Fuchsian group. Anyway, so. But this is already, and then, so in other words, this category or context has been very fruitful in mathematics, obviously, but it's sort of arose, and in a sense, Gauss's theorem was, which could modernly be formulated to be said like this. So question, might there be, let's say, is there any analog in 3D? So, well, this is an open-ended question, but so something about the general 3D manifold of a certain class has some structure that can be expressed in terms of coordinates, and presumably this expression will be useful for something. That's sort of what the question means. Okay, and there's some evidence, which is another remarkable theorem. There is a remarkable theorem in 3D. The remarkable theorem in the remarkable geometrization theorem and although it goes beyond this, it doesn't go quite as far as what's indicated there. So I'm going to restrict to closed manifolds now, instead of arbitrary open manifolds. And though that's an interesting area to push the wonderful story behind this theorem further into that domain. It's open. But anyway, remarkable geometrization theorem of, and this will be my own version of the history of Thurston, Hamilton, Santiago here? Hi. Hamilton was with us in grad school, right? Richard Hamilton was with us in grad school. Don't remember? He was in my class. So, well, he drove a '63 Corvette, and he did windsurfing all the time. He was never around, so maybe that's why. Anyway, Hamilton, Richard Hamilton, and then Perlman. And then I'm going to write the theorem. I'm going to write a kind of, casual statement, vague statement. And I'm going to put in oriented I had over there, even though a lot of this could be changed. Every close. I always like manifolds to be connected, so I'll put that into every closed oriented 3D manifold can be by the way, in dimension 3, you can think of the manifold as being topological or triangulated or smooth. Those categories are all equivalent by some interesting theorems of Moïse and Bing in the 50s. Can be canonically, so I don't have to say smooth or anything. Can be canonically decomposed. Into pieces separated by low dimension 1 walls. That are either two spheres or two tori. It's canonical, if you say, put the right conditions, it's sort of minimal in a certain sense, stuff like that. So that each region each region of the complement walls carries a homogeneous 3D geometry. And I'm going to, this is not well said, but it gives the idea. Now, so this, the more elaborate formulation is due to Thurston, who actually proved large parts of it. The formulation actually, so this is like 1980, the formulation actually contained a piece that included a strong form of the Poincare conjecture, which interested Hamilton. So he introduced the key tool of partial differential equations, and Alberto already said the name of it, the Ricci flow. and worked on it for 10 years till 1990, and he was interested in using it to prove the positive curvature part of this, which is the Poincare conjecture, and he got some theorems, but he didn't really get the thing. And then Perlman visited him in 1990 from Russia. He was a postdoc at Stony Brook, and Hamilton shared all the information where he was stopped, and then Perlman went back to Russia, worked for 10 more years, and then proved the whole thing. That's sort of. But Thurston had already proved like 80% or whatever, 90% of the complement of the Poincare conjecture, but already around 1980. Okay, so that's sort of. Okay, so that's like evidence. So this is a general theorem. It's about all closed three manifolds, and it extends beyond that quite a bit to things like not or link complements, and it's quite remarkable. So that's my evidence. There should be some analog, there should be some kind of structure in 3D. There might be some kind of structure in PD that sort of unites, and these geometric pieces is something discovered by Thurston, which is here on the blackboard. There are 8 geometries discovered by Thurston, and I have pictures. There's no notation. If I erase this, there's nothing on the board except pictures now. Okay, that's important for me. These are pictures, and I'm going to just quickly say what these pictures, how to think of them. And then at the same time, say what Thurston meant by a geometry. So the geometry in the sense of Thurston, and there's exactly 8 of them, and 1, 2, 3, 4, 5, 6, 7, 8. It's a 3-dimensional homogeneous geometry, Riemannian geometry, complete, homogeneous, and it admits a discrete group of isometries so that the quotient is a compact manifold. That's the definition I'll use here. And now I'm going to sort of tell you what the geometry is. This picture is supposed to suggest how you find a compact version of the geometry. Okay? So the idea of this one is you have a plane moving around a circle, but as it slowly moves, there are 2 directions of the plane. One is being stretched and one is being contracted. And as you move around, you get stretched and contracted, and then you come back with some discrete version of that, the matrix 2, 1, 1, 1, something like that. So that's a picture of the geometry. And you can take these lines and put them at irrational slopes on a torus, and then the matrix 2, 1, 1, 1 will act on the torus, stretching the one foliation this way and contracting the other that way. And I think the eigenvalues are the golden number and 1 over the golden number, 1.6 and 0.6 approximately. So you can think of this as a torus moving around, subjected to this monodromy map. And its universal cover would be the homogeneous geometry. And then here you go around. This is my attempt to draw a shear. You take like a rectangle and you just shear it. So you go around, and when you come back, you have a unit shear. And you could think of this as the fundamental domain of a torus also. So these are affine geometries. And then we have couple of round ones. So this one is the two-sphere cross R. So the two-sphere can be homogeneously rotated, and you slide it along in the R direction, so that's homogeneous. How can I make this compact? If you have to under 30. Only people under 30. Are you under 30? No. Under 50, what the hell? No, you're not under 50. What? No, are you under 50? I don't know. No. Dick, are you under 50? Yeah. You are? Okay, can you say? Yeah, right. Just cross with the circle. Take the sphere, and the universal cover of the circle is R. So this is it, geometry, right? Okay, now this one is more interesting because it's going to appear there are two versions of this. You take the round two-sphere and you make it, it's two-dimensional, it's not three-dimensional. And then you just take the unit tangent vectors. That's a circle at every point, and you spread that around, and that will be a homogeneous geometry because it's clear, because you can move the sphere all around. And this is compact, not quite simply connected. It's the projective free space. Take the double cover, and then it's simply connected. Anyway, you don't get an infinite thing. So this is the only compact one? Yeah, I guess. This is the only simply connected one which is compact, I think. Okay, but then you can do that. Okay, this is the dual of the round geometry in dimension 2 is the negatively curved geometry. This is supposed to be a picture of like a mountain pass. So drive your car over between two mountains. Drive your car over like that. So this is what a piece of hyperbolic space looks like. And this is homogeneous. You cross that with R, and that gives you a three-dimensional homogeneous geometry. And there are plenty of Fuchsian groups acting discretely, and quotients give you all these compact Riemann surfaces. So this, and do the circle here. And then, now, take this hyperbolic geometry and do this circle business. Put the unit circle everywhere. Then that'll be another geometry. Again, the Fuchsian group, a discrete subgroup of isometry, will act on this and give you something compact, which is like a unit tangent bundle of a Riemann surface. Okay, so that's 6 geometries. Then we have, what's obvious geometry we didn't say yet? The one we sort of seem to live in, right? Euclidean geometry, right? So I've represented that by a cube. Everything is flat. And then it's hard to draw a picture of H3. I mean, you can give models, but we learned when Thurston arrived on the scene in 19, he completely changed everyone's world outlook about the models don't really properly express what it feels like to be in the geometry. And he started to explain how to live in the geometry. He just automatically lived in the geometry. So to really understand this geometry, you can give models, which we're going to use later, but you can give models, but the real important thing in this geometry is the what are called the horospheres, which is like I'm on the circumference, I'm in hyperbolic space, I'm on the circumference of a sphere of radius 1,000,000 miles whose center is way over there. And then now I'm on the sphere of radius 100 billion miles whose center is way over there. And it turns out these spheres, as opposed to Euclidean space, stay curved in every direction by a definite amount. Curvature is greater than 1 if you have curvature minus 1. So the limit, as the center is at infinity, is a nice infinite radius sphere passing through me. And if I step forward one, there would be another one like this. If I step backward, there would be another one like that. So they get these foliations of hyperbolic space in every direction to infinity. And that's the real thing to understand the geometry, in my view. Okay. So that's H3. So we have them all. There are only 8 homogeneous geometries that admit, in dimension 3, that admit discrete subgroups with compact functions. And these are those. And this theorem says that every closed 3-manifold can be canonically decomposed into pieces which have walls given by spheres or 2 tori, so that the regions in between carry these geometries. And I'll be more specific about that. And the kind of picture, I don't like this picture too much, but it sort of looks like this. The round, so it turns out that see, we're given a whole bunch of 3-manifolds here. This one divided by its discrete subgroups, this one divided by its discrete subgroups, this one, this one, this one. Well, these are not so hard. These are S2 cross S1, essentially, the manifold. All of these are quite complicated. These are flat 3-manifolds, like 3 tori, or things that are finely covered. And then this is the unitangent bundle of Riemann surface. This is circle across a Riemann surface. So we get a bunch of these pure manifolds. This one is quite interesting. This is the group of isometries here contains, it's got another circle factor, but it's basically PSL2R. And PSL2R is bijective to this just by choosing a tangent vector somewhere. And you see where the tangent vector goes, and you see how it turns, and then your orthogonal vector given the orientation gives you a frame, and that completely determines it. So these are interesting. And then we have, Thurston's work was mostly about these hyperbolic 3-manifolds. So many, in fact, we had a talk where the figure 8 knot carries one of these. Although, you might have wondered why I put this line here. Putting this one aside for a second, these 3 also carry finite volume. Besides having co-compact subgroups by definition, they carry finite volume things, because you have Riemann surfaces with cusps. And these can have 3-dimensional cusps. And this one has small volume. I mean, besides the compact one, there's small infinite volume. You can have a torus cross a line, so it just has linear growth. So this is very small, still not finite. But I think of these 4 as coming into the hardest step of oh, by the way, this talk is really, if there's a theorem here stated, it's like an observation or an exercise. It's not really a major event of anything. Okay. It's sort of like a PR. I want to have a formulation of a big chunk of this theorem that's precise and short and catchy or something attractive, not just, I want to say, all 3 manifolds are covered with, butter or something. I don't know. Some delicious butter that you can only get in Cuernavaca or something. Anyway, okay, so this suggests there's some texture that we can say about dimension 3, some texture. So what is this? So that's sort of, been thinking about this a long time, and some say, okay. Now, so there's a whole bunch of 3 manifolds you just get from this statement, just all the ones you get from the geometry by dividing by a discrete subgroup. So I'm going to so I'm going to think of those as, I'll just draw those like round things like this. These are compact manifolds with a geometry, a pure geometry. These are pure, one of the 8 pure geometries. So they involve arithmetic and stuff like that. like these correspond to isometry class, commensurability class of these correspond to real quadratic fields and stuff like that. That's something Alberto and I worked on, right? Anyways, and these, all of these subgroups here this geometry is unique given the topology, even given the fundamental group. If it has a hyperbolic metric, it's unique, and then all the generating elements of the fundamental group are given by matrices. The matrices are algebraic numbers because they're isolated points of algebraic equations defined over the integers. They're not quite arithmetic groups, but they're arithmetic in the sense that the coefficients are algebraic. This has got a lot of arithmetic. Okay. And then there's another thing. These three have finite volume. These three have finite volume things, which I'll sort of draw like this. They have finite volume, and it looks like a torus. This end here looks like it goes on forever like that, and it's shrinking down. So this part is finite, and this torus is here, and this torus has a conformal structure given by the metric. So, and again, these are unique given the group. So given the group, there's an elliptic curve, coming out from the fundamental group for each end. If you have more than one end. So these I'll draw like that, and then. So all of them look like that, and these are the torus walls. So you sort of cut off the, and then you take these three kinds, and you have three kinds, and then you can glue them together in various ways along the tori, according to any graph, actually. And if you say any graph, you have to do something with isolated vertices that are univalent, and then you use a long cylinder, torus cross I, and then you fold up the torus using a Klein bottle. Anyway, so that's not important for now. So anyway, so I want to think of these, and now I want to draw something here which is important. Let's see, maybe I get it right. So these things are sort of like this. These horospheres I mentioned, when you have a discrete group of finite volume, there has to be a z plus z acting on the horosphere to fold it up into a torus. And these toruses are rescaled as you go down, so the conformal structure stays the same. And horospheres are intrinsically flat, as I said, because it's like a sphere of infinite radius, so it's intrinsically flat, but as I said, it's curved, and the curvature doesn't go away. So I'm indicating that by this picture here. Okay. Curvature. Okay. Now, so they're decomposed into pieces that are geometric. So in fact, this name is slightly unfortunate from my point of view, because the theorem does not say that there's a geometric structure on every three manifold. It says it has canonical decomposition to pieces, and then you have to glue them together. And the way you glue them together is potentially nice, but it's not completely nice, because well, these metrics are all real analytic, so if you have an open set that has negative curvature and then you want to combine it with something that has zero curvature, an analytic function can't be constantly zero here and a negative over here. So it's clear you can't glue them together geometrically in the Riemannian sense. So there's already, if you want to make this shorter statement, the technically correct statement, you've got to change the notion of geometry. Okay, but topologically, we want to cut this off and get a torus thing, and maybe we have another one coming in, and let's say, let's make this bigger here. Okay, so we cut it off. I mean, if you just cut it off, if you cut off two manifolds of boundary and stick them together, that's not, the analytic structure doesn't go across the wall. You have to say what the analytic structure is in the transverse direction, right? So if you just glued these two together like this, you would be, say, where this part, this part goes to here and this part goes to here. That would be a way to glue them together smoothly to get a smooth structure, right? But you see, let me draw this better here, sorry. You're sort of, it's like you're putting sleeves together like this. You're sort of sticking this onto that. And you see they're curved in the wrong direction. You're trying to stick a bunch of things like this and a bunch of things like this together. Because the curvature is obstructing this process. You've got to flatten this out somehow. You're going to do the gluing. And if you want to do the gluing and have it be, you want this to be sort of geometric in some sense after you do the gluing. It's gluing on each piece, right? Okay. Okay. So, that's one of the things. And then the other thing you have to do is, this is the torus gluing. This is torus gluing. Torus combination, I'll say. And then the other thing is, if you wanted to glue two of these together, you have to do what's called a connected sum. Take this one and want to do, and this sort of means you just let touch, kiss at one point, and then you just open this up and cut a little hole out here and a little hole out here, and then make a little tube that goes across. You make a connected sum. The two-sphere cross I, so this becomes a manifold. But basically, it's arbitrarily small, so it's really just touching like that. So then, this picture of the theorem says that any closed three-manifold kind of looks like this, namely, it has the first step is you take a bunch of manifolds and you just glue them together with connected sum. And I've drawn two kinds, roundy ones and sort of funny shaped ones. The roundy ones are supposed to be these pure ones over here that have the pure geometries. And the gluing locus is this two-sphere here. And I haven't said what the big ones are yet. And then the big ones are, they're divided up. They have, the big ones are something like this, but they have torus walls. So these are toruses. And then each piece here is a manifold whose boundary is a finite union of tori. And the toruses are glued together. And there'd be a dual graph to this. I didn't draw a very interesting dual graph. And the graph could be arbitrary. And the labels are the different finite volume geometries you use. So the statement takes a while to formulate. How am I doing time-wise? Huh?
Half an hour.
No, but what's the actual time?
5:25.
Oh, okay. So I'm supposed to go to 6? Oh, well, 5 of 6?
That's right.
Okay. All right. Yes, please.
Pick any one of the geometries. Does it have a preference of the wall, the type of wall you can have?
No. The topological way to say it is if you take one of these pure geometries, you can take any connected sum. Take 20 of these, like oranges and apples, and just make a necklace out of them. Do a connected sum. No, the walls are two spheres then. Okay? So that's why I have to say more, because if you do a connected sum, what I mean is this topological manifold, which is secretly a connected sum of two geometries, what I do is, I'm formulating it, that means it's obtained from a nice geometry by removing a disk. And then I just put the disk back on each one, and then it's its original self again. It has a pure geometry. Then I take the disk out, take the disk here, and then I have boundary of two-sphere, boundary of two-sphere, and I glue them together. Topologically, so that's what it means. This is one two-sphere wall with a pure geometry on each side, but after you complete it by gluing in the hole, filling in the hole. And then over here, when I have two like this, I mean the wall is a torus, and you just think of naively, I take the torus here and just stick it under the torus there. Then I cut that torus out, and then I cut it with an infinite cusp, and then it's one of the pure geometries. So that's the sense I mean. I didn't say any of that. Okay, is that okay? No, but in the graph, when I say the graph, I said I could use any graph. Where is that picture? Oh yeah, here. These guys here are the, I could simplify this discussion by talking about an old theorem of Van Kampen and Milner called the unique decomposition into primes. Every closed three manifold has unique decomposition into connected sums of manifolds which are not connected sums themselves of non-simply connected manifolds. That's now is the correct way. That's the correct statement now after Perlman. But and then those primes are unique topologically. There are two kinds of primes. The round primes, which have the pure geometries, and I'm about to describe the mixed primes. Okay, I haven't gotten there yet. Although this. See, this decomposition, these two decompositions, it's a little like chemistry. This decomposition is very weak. It's just like two kiss at a point, right? This is, they share a Z in the fundamental group, which is a subset of the fundamental group. You stick them together, and that piece of the fundamental group is being shared. This is a very rigid thing. It's like covalent bond in chemistry. It's possible to break a covalent bond. This is like an ionic bond. It's just, you can slide it around, and somebody could come and track this away. I don't know. So this is a much stronger, these manifolds are still prime. They're not connected sums. Okay? So this is like a covalent bond. This is like an ionic bond. I have other names. Okay. So anyway, I'm discussing the still. And so these are the atomic primes, and these are the molecular primes with these covalent bonds. So I took this one here and I redrew it here, and I drew this funny thing here because the torus boundary, which is the wall between them, from this side it's convex this way, and the one I want to glue is convex this way. So there's something wrong. They don't fit together. And I mean, this is so it's topology. I could just glue this together, but then the geometry, I've got to distort the geometry. So the idea is to, okay, so now, so the challenge is to combine the various geometric pieces of this canonical decomposition in one context, one sort of geometric context. Like this, it says you can glue all these manifolds together with coordinate charts where the overlap transitions are in this context of complex analytic functions, not just use diffeomorphisms. Okay, so that's, is there,
Like a kind of a new geometry combines.
yeah, well, it could be that, or it could, could be
So in other words,
some ideal theoretic concept also, or some logical concept. I don't know.
like a uniformization. That'd be like the ultimate.
Well, I'd like to use, not literally the uniformization, but uniformize the discussion. Make it uniform, yeah. Make it in one context, and combine the various, so the pure geometries have to be absorbed into like socialism or something, I mean, all the different businesses or something, into one context, all these pure geometries. Then, that's also, and actually, it's been known since the 90s how to do the 8 geometries into one context, even before the conjecture was proven. I'll mention that in a moment. And A, combine, and B, well, combine the regions between the walls in this context. Combine the regions in this context. So I'm using the word context for what you were saying, some new kind of geometry, okay? Just a new context. Like this is, well, you could say this is conformal geometry, right? That could be, but maybe you don't know, maybe you didn't know that maybe before you had these things, you had examples, didn't know that, didn't know about differentiation. Okay, so, where's the eraser? Okay. Okay, so that's the challenge. Okay, so this is the point. We will describe how to do this in the context of Alberto. Yes. Yes. Divinar. Is that Spanish? Divinar? Huh? Guess the context. It was in your talk. I got miffed at his talk because the surprise goes away. Huh? What? In the context of quaternions. Yeah, right. Okay. 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 Okay, so let's discuss quaternions. You helped me. You told me some new things. Because I couldn't find all of Alfor's papers. I was too lazy to look, so I was just thinking about it. And I don't have any corollaries. This is a few days old, actually. Let's put it over here. Okay, so I'm going to repeat some of your talk. Okay. So we'll call this H, and now, I just erased the remarkable theorem. There was a C here. This role of H will be different from the role of C, because that's an unrequited dream of mathematicians in the 18th century, the 1800s and in the 19th century and the 20th century, early 20th, to make an analytic theory of quaternionic functions. It's an unrequited dream, and we'll show why that dream doesn't work for some aspects. So H is, as a vector space, it's R4, 1, I, J, K. I'll erase this now. I'm not going to write too many formulas. It's a non-commutative and associative, has a non-commutative and associative product, and an anti-automorphism, or product, dot, and an anti-automorphism, like you can form X times Y. It's non-commutative and associative. And you have anti-automorphism, X goes to X bar. So A, B bar is B bar, A bar. That's what anti-automorphism. And X bar is like a norm squared. And this is on R4, a nice positive definite metric. So we have geometry in R4. And it's an anti-automorphism, so I'll write that down. A, B, bar is B bar, A bar. Okay. And then here's the kicker for the unrequited dreams. The map, there's a, given A and B in H, we could define a map. X goes to A, X, B. I don't have to put parentheses because it's associative. And this is a map from H tensor H. Now there's an amazing fact that associative algebras have a tensor product. This is also an algebra, right? I find it amazing because Lie algebras don't have an associative product. So, and this goes into HOM HH. And if you count dimensions, this is 4 times 4, so it's 16. This is also 16. And this is an algebra isomorphism. This is an algebra map. Wait. Anyway, this is a bijection. And this is also how do I write this? So this is a bijection, this map, so that if you wrote down a formula involving quaternions, like something times x squared, something times x cubed, then you have to put the coefficients. You could try putting them just on the left, but then you couldn't multiply two such power series because the coefficients would go on both sides. And you couldn't compose. So you have to put them on both sides. Then you could try to develop a theory of such power series, but then the linear approximation gives you all 4x4 real matrices, no conformal property. So if you developed that and took the closure, you would get all diffeomorphisms. Okay? So if I were doing it that way, this would not have any content. If I were doing it that way. Okay, but then you can do nice things. There should be a way to do that. You can do nice things with simple formulas, like you wrote down some formulas. You got all the conformal maps of the force sphere, like linear fractional transformations, right? It's non-trivial and non-obvious, right? Okay, and interesting. Okay, so here's step one. I'm going to describe now. It's going to have two steps. Okay, well, oh, and because of this, every non-zero quaternion has an inverse, right? X can solve from here. So let's just think of these linear operators defined by quaternions acting on R4, acting on lines through the origin. And then we take the space of the set of lines through the origin. This gives us real projective 3 space. Oh, I should mention this is an involution, involutive, so it breaks the quaternions up into, what did you call them? Somebody called real. The real part, which is the center, and then the purely imaginary part, R3. So this is where we're working in 3D. We're going to use quaternions in 3D. So we're going to work in this part as much as we can, but this part comes in the formulas. And then you also have this other way to get to 3D by taking the space of lines through the origin. So these operators give you all the projective isomorphisms. So from the quaternions, we get all the projective isomorphisms in 3 space. Okay? Well, it's known, there's a paper by Emile Morland, maybe not the right name. Where's the speaker? Who's from before? He's from Hungary, right? Renyi Institute, is that Hungary? The speaker from before. Before this one, just now. Where is he? There. Are you from Hungary? No, but I mean, you know about it, right? Okay. Do you know this name as a Hungarian mathematician? Okay. Anyway, he has a paper in the 90s showing in a nice concrete way that all of the 8 Thurston geometries with their group of isometries, those groups of isometries are subgroups of the automorphisms of projective 3 space. So you can kind of absorb the 8 geometries into one context. So here, it's projective geometry. Okay, that's the context there. So, you know, you could try to show, well, maybe all of these manifolds that have these geometric pieces, they can all have projective structures that are compatible. So you can talk about straight lines. That would be a dream theorem. I would be happy to prove that. Unfortunately, Goldman has already proved you can't prove that. He's a party pooper. Huh? Yeah. Yeah, but he has a restricted definition. In that restricted definition, which is the nicest one, he's a world expert. Yeah. Okay, so that's a rough idea, but now I'll show you why well, these two geometries are affine geometries. Affine geometry is contained in projective geometry. So this is okay. This is already RP3, so that's okay. This is obvious too. Oh, this is Euclidean geometry. Rotate the sphere. Huh? Yeah, right, okay. Yeah, the unit quaternions in, yeah, yeah, right. And then let me show you this one, which is interesting. This one is the Klein model. You can take the 3-ball in Euclidean space and just, the geodesics are just the straight lines. I mean, the projective lines are just the lines. And there's, it's nice proof of this using stereographic projection and projection from infinity. I don't have time now, but it's nice proof. And then you can even get the metric, hyperbolic metric, by the so-called, by taking the logarithm of the cross ratio of these 4 points. Take 2 points anywhere, draw the line between them, get 2 more points, look at a log of a cross ratio, and that gives you the metric. And it's invariant under all these projective automorphisms and so on. So that's how projective geometry contains this very interesting example here. And then the 2-dimensional version does these 3. Euclidean is already part. And anyway, more or less done. Okay? Okay. Now this has a negative feature, which is the projective geometry knows about the actual geometry because you can construct it in the context as the cross ratio. Okay? So therefore, when you try to hook 2 of these hyperbolic guys together, the projective structures that I would associate by dividing by discrete groups, they say, no, you can't glue these together projectively because I know the metric from the projective structure. And these are curved this way and those are curved that way. Can't do it.
What if you take another projective structure?
What?
What if you take another projective structure?
I don't know. But I mean, this is casual. You might, there are some instances where a perturbation of that projective structure, there's a paper by somebody involving wrinkles, and if the wrinkles fit together and the gluing map, I've got to also accommodate any affine gluing of the torus. And this paper didn't do that. So I have to accommodate all the affine gluing. So that paper did that. So, but let's just sort of be reasonable. There's a natural projective structure. It doesn't want to, right? So, okay. So we need to we need to bend that convexity out. We need to bend it out. So, to continue. So, step 1. Yeah, so this already, projective geometry contains all of the 8 geometries. So I'm in the, so I've got, all of the round atoms, but I don't even know how to make them kiss because still there's convexity. In fact, if you took a neighborhood of a point in this manifold with a projective structure, you could think of it as locally in affine space. You have these concentric spheres, and then it sort of looks like this. And I want to cut off a sphere here, cut off a little sphere here. And I want to glue this part to this part and this part to this part to do the connected sum. And already Kuiper in a 50s paper in the Annals showed that if you had inversions in your toolbox, you could do an inversion in the middle sphere here and interchange the roles of the convexity and then do this gluing together. So let's see, do we have, in the quaternionic world, do we have the inversion? Obvious, yes. We have, take a sphere, and I can think of restricting attention to the imaginary part. I can do the whole thing, or restrict attention to the imaginary part. And then you have the map x goes to, let's say this, 1 over x. It's roughly the inversion. There's have to put a bar. Maybe I have to put a bar. Huh? Anyway, I can define the inversion. then I could, in this context, I could at least do all of these gluings. I could do all of these. But I can't do these unless, because these are the torus gluings. Okay, so then, this is step 2A. So A would be doing connected sum. And then B, I want to do, so then, how am I doing now? Time's up? Huh? 10 minutes? Okay. So, well, then you just, I'm only on, okay, so, okay, good, 2/3. Okay, so then there's an inversion like this, and I'm going to write a formula. I'm going to square A plus B. Oh, not quite. Okay, so what I want to do is define this map. I want to take my center of inversion to be, this is a fixed point, like take the point 1 at the standard. This is a sphere of any dimension alike, but I'm thinking of the 2-sphere. That makes sense, any sphere. And then for all the lines through this point, I'm going to do that, and then I get another point, and then I'm going to take this point to this point by a kind of analogous to the cross ratio inversion. So these are so-called harmonic points. In fact, I could, I want to invert in the sphere of this radius, and so this point here, if this distance is c, if this distance is c, then I'm going to map x, this distance here, this goes to c squared over x. So this is, x is a quaternion, and it goes to c squared over x, where this distance here, I'm in Euclidean space, this distance here is c, and I do c squared over x. So x goes to c squared over x. And then on this line, the c changes, and x goes to c prime squared over x. Okay, so this is not a single inversion, it's a varying inversion. What? 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 Yeah, right. So, yeah, I'm doing inversion about a point which is, so I'm going to invert just this, I'm going to talk and give the answer. You said repeat. I'm repeating. So this distance, I'm in Euclidean space, this is the unit sphere. This distance is called c, and any point x here is going to go to, this is a quaternion, though, goes to c squared over x. X here goes to c squared over x. Just on this line. On this line, I have a new c, and x goes to c prime squared over x. Okay? So it's a varying inversion, but it's in the context of hyperbolic geometry. And then if you consider all the circles tangent to here, then if you, this map, this was the original circle here, then this is the original circle, and this inversion will move this region to this region, and it gets thinner and thinner down here. And this will be, allow me to, that inversion will allow me to do these cuffs together, because this is, in the projective model, this could be related to the upper half space model where the horospheres are horizontal planes, and you could do that in the projective in the quaternionic context. And then the discrete group that makes this have finite volume has to have a z plus z subgroup here. So this horosphere becomes a torus. And this inversion, this family of tori are these family of tori here, and this inversion is doing what I want. That's sort of the idea. So you have to have stereographic projection in your context and these formulas. And the one I wanted to just, let's say here, I want to think of this as the unit sphere. Well, let me just do it again. So this is like a fixed point. This is the unit sphere. And then this is A, and this is B, and this is C. And then I want to compute C squared, which is equal to, so I think of these as vectors, and think of this as a vector, this C here. And C squared is A plus, as vectors, it's A plus B, as quaternionic, the vectors, right? Times A bar plus B bar. And this is equal to A squared, A bar, plus B squared, B bar, plus A bar B plus B bar A. Did I do that right? Oh. Anyway. What? What? No, BA bar. Yeah. BA bar plus AB bar. Okay, so this is, let's just call this, let's just use A's again. So this is what we learned in high school. Remember the name? No? Huh? What? No, you don't learn that in high school. The law of cosines. When you work this out and so on, the directions and so on, this will be the minus 2ab cosine theta, right? So we have, in the quaternionic context, we have all of high school geometry, law of cosines. We can write out with formulas in terms of the, so, and then when you need the stereographic projection too, which are similar formulas. So that's right. Okay, so then here's the takeaway. Erase this. So the takeaway is so using the algebraic structure, the high school algebraic structure of the quaternions, we can build projective geometry with the ax plus b, where the x goes to axb, build projective geometry, and then we can build the two gluing operations that we need. Using the algebraic structure, we have a context. To reproduce the geometries, the 8 geometries, and the 2 combinations of the geometrization theorem. And then, last thing is that's the challenge then. So we've done this challenge. Let's make a new challenge. And also, the operations that we use in projective geometry are very low order. They're sort of division and quadratic. Like, it's quadratic in the numerator and division in the denominator. So it's sort of, and the first step was linear. X goes to A, X, B. That was linear. And then we have quadratic and dividing quadratic by linear, right? So, so the challenge is study this concept. Oh, by the way, and this is just an observation. This theorem that I'm using, that you get all manifolds, is 100 years of incredibly extreme genius mathematics. 100 years. Poincaré and all the topologists, Thurston, Perlman, Hamilton. So this is like an observation using all that material. So it's like quaternions and a low degree algebraic discussion with quaternions, okay? Then you can describe all three manifolds. So study this context. Oh, and then I have a historical note, which I've indicated already. Earlier attempts to generalize C to H did not satisfy the goals. They were usually trying to do in 4D, trying to extend directly from 2D to 4D. And 4D is completely different in the theory of manifolds. 3D is sort of the last dimension when everything is potentially constructive and decidable. And so I think there's an element of logic that comes in here, which is almost like Ernesto's talk, which is decidability, finite decidability. In other words, you only use certain properties of quaternions to make this construction. So what does it mean exactly? It's not all of algebraic geometry. I'm not taking all rational functions. That's too big. With that, you could do every dimension. So, and my particular question is to study, so remember back the original remarkable theorem was there are coordinate systems that work for all two manifolds. So here we have coordinate systems that work for all three manifolds, closed three manifolds. So they generate some theory of diffeomorphisms in dimension 3, which has limited distortion because you only use a few formulas from quaternionic algebra. And maybe you can study some other problems. And maybe I'll burden you for 2 more minutes. I got very excited by Perlman's work because even though the Ricci flow, I've been studying this Navier-Stokes equation for, it's got a quadratic term in U plus a constant times the Laplacian of U, studying this equation. And this quadratic term has got a global aspect, so it's deceiving. The Ricci flow is, G dot is the Ricci tensor, and he takes -2. The Ricci tensor has 2 indices, the metric has 2 indices, and so it's a tangent vector to a metric at every point. So this is the Ricci flow. But when you compute the Ricci flow itself, turns out it satisfies, it's got a quadratic term, RR, and plus Laplacian of R. So it's not dissimilar to the Navier-Stokes equation in 3D. And I got all excited, and I said, no, and my excitement said, and he cuts off places where this blows up and continues on and proves this theorem. And it's a little problem because this quadratic term, this is the quadratic term, Q of R plus the Laplacian of R times the constant. So I think, anyway, so I'm hoping that this, or possibly deriving something from this, can help you get a better pseudogroup in dimension 3 that will help you study this equation. That's the end. Thank you.
Any question or comment?
Yes.
Who?
And you
this is if you want
Want to combine them.
if you want to take a region with a geometry A and a region of geometry B, and you want them to kiss, couldn't it happen that geometry C could be
No,
could we put a little
No,
strip?
I'm taking A and B and putting it in context Q. And I'm gluing in context Q. And see, I showed you what the geometry, if you can build a model of hyperbolic geometry in dimension 3 this way. It's inside quaternions, like Euclidean space. And well, I mean, first you get projective, sorry, so I skipped a step. I use linear quaternion automorphisms to reconstruct the automorphisms of projective geometry. And then I model in projective geometry, one models in projective geometry, hyperbolic 3 space. And then these could be 2 hyperbolic 3 manifolds. Then I construct with quaternions the first inversion, and that's how I glue. Now that's not a projective transformation. It's in the context of quaternions, though. So you can't do it in projective geometry because I said one's bending this way and one's bending that way. That's a metric invariant, but the projective structure remembers the metric. So I have to break, I have to, kick it. You have to kick it 2 ways to do the 2 gluing steps.
But in the 2 discs that
Wait, let's
Don't do
spread the
kiss.
questions around. Yes, for your second question. Okay.
I don't know about this. Not same question. You have there 2 regions that are going to kiss. 2
Oh. No, here the kissing is done, this is Kuiper's argument. I explained that here. In the projective structure, I can think of a radiant projective structure, radiant affine structure. So, yeah. So I think of projective structures. So locally, it's affine space. Locally, it's Euclidean space. So I think of concentric spheres around the origin. And then I can think of this like cone-like thing, concentric spheres also. And then I can draw these cones like this, cut off a little bit here, cut off a little bit here. Oh, sorry. Cut off a little bit here and a little bit here. And then I use the inversion to relate this one to this one and this one to this one. So this is, when you do connected sum, there is an orientation reversing operation there. So you have to think, I think about this every day, but anyway. So if you have an inversion inside your geometry, so when you have conformal transformations, you have inversion. So you can do connected sum inside conformal geometry in dimension 3 free. This is a Kuiper's paper from the 50s.
Okay. I think Kulkarni
What?
Kulkarni has all this theory of conformal, connected sum of conformal. What?
What?
No, I mean Ravi Kulkarni has a whole book on conformal gluing using inversions.
Yeah. But see, not all the geometries, only 5 of the geometries are
Yeah.
inside conformal geometry.
Exactly.
3 of them are not. What?
But you can,
What did you do? You drew this? Yeah, but no A, no B. I'm throwing away all the A geometries and replacing them with projective geometry.
So you have solution for this case.
okay. Bueno, muchas
What
gracias.
is
Thank
this
you,
page?
Dennis.
Oh, you have 3 geometries?
I think we should thank you for your talk. We should thank the speaker. Thank you, and I think Alvin is going to take a picture.
Please, no, no voy a cantar, Javier. I will ask you to gather together closer to take a picture of all of us. And I asked Pepe and